Previously, we had stated the first law of thermodynamics, which said that the change in thermal energy of a system is equal to the work that is done on the system plus the heat that is transferred into the system. So this is purely a statement of energy conservation. But we're going to take a look at some different thermodynamic processes and examine them in light of the first law. So the first of these processes I want to take a look at is what's called an adiabatic process. So the hallmark of an adiabatic process is that there is no heat transfer. So what would such a process look like? We could envision, say, having a very well insulated piston. Well insulated piston. And like we were talking about before with the quasi-static process assumption, we could imagine having a stack of coins here. Got my gas here. And then, for instance, I can go and take the coins off one at a time. And what will happen as I take the coins off is as I reduce the pressure, the volume is going to expand. Or if I add coins, it'll contract. All right. But from the first law, since delta E thermal equals Q plus W, if Q is 0, then for an adiabatic process, turns out that all the work done on the gas will correspond to a change in the thermal energy. So as this expands, what we'll see is the gas cools down, the thermal energy decreases. Now, the PV diagram for such a thing looks something like this. So in this example here, where we're doing an expansion, so here's P initial, P final, V initial, V final. The process is going to look something like this, and you might think that this looks like an isotherm, but it's not. The pressure here is not proportional to 1 over the volume, but instead the volume to the negative gamma, where the value of gamma will depend on the gas. We'll calculate this later. A typical value is 5/3. So the pressure in an adiabatic process falls off as the 5/3, inverse at the 5/3 power of volume, or some other possible powers that we'll get to later. As opposed to an isothermal process that falls off as 1 over the volume. So this falls off more rapidly than isothermal, which makes sense. Because in this example here, the isotherm would be, that goes through our initial point here, would look, say, maybe something like this. And since the work done on the gas here in this expansion is negative, what we have is a negative change in the thermal energy, which means the temperature will have gone down because the gas got cooler. So it makes sense that we ended up that this ends up falling off faster than what an isotherm would do. All right. Let's take a look at another example. we can look at an isochoric process, or a lot of books will call this isovolumetric, which is probably a more useful name. So remember, with any of our iso processes, the iso prefix means the same. The same what? The same volume. So this is a process where the volume doesn't change. So we could just imagine having a container here, and I don't know, we go ahead and seal a container. We go ahead and light a Bunsen burner underneath it to help transfer some heat into the system. That's just going to serve to make the gas molecules inside the container more agitated. Okay. So the PV diagram for such a beast is going to look something like this, where the volume initial and final is the same. So in this example I've done here, where I've transferred heat in, the thermal energy of the gas is going to go up, and so it's going to end up hotter. And so since the volume isn't changing by the ideal gas law, that means the pressure is going to have to go up. PV equals nRT, V is a constant, P and T are proportional. But the important bit here is that the area under this curve, whether it's a heating or a cooling, is zero. So this means that the work done on the gas, or for that matter by the gas, is zero. Now, since by the first law, delta E equals Q plus W, if W is zero, in this case, all the heat is going just to change the thermal energy of the gas. So if we're transferring heat in, the temperature goes up. If I say have this stuck on a whole bunch of dry ice blocks or something to help transfer heat out, then the temperature would go down. All right. Now, another one is an isothermal process. We've seen isothermal processes before. So in an isothermal process, iso, the same thermal temperature, the temperature is a constant. Now, I haven't proved it yet. That will be coming in a later video. But if the temperature stays the same, we've already argued, and will rigorously prove later, that if the temperature is the same, by the 0th law of thermodynamics, that means that there's no heat transfer occurring. So that would mean that the change in the thermal energy of the gas is 0. So for something like this, I would be bringing back pardon me a moment here. For something like this, what I would be doing is taking our piston like this, and we'll have our gas and our stack of coins, but this time it's not going to be an insulated container. Instead, we're going to put the whole thing in a tub of ice water. So I'm just drawing in a few ice cubes here. Something like that. So the whole thing's sitting in a tub of ice water here in order to maintain a constant temperature, in this case 273 Kelvin. So as I take a coin off, the gas would want to cool down. We saw that before when we were thinking about an adiabatic process. However, what will happen is we'll have a heat transfer in from the big tub of ice water. The official name for big volumes that we can keep at a constant temperature. We usually call this a thermal reservoir. And either it's so big that practically speaking the temperature doesn't change, or in this case with the ice cubes here, we can just simply freeze a little bit more water to make more ice in the volume here in order to release heat to transfer in to the piston. In any event, by the first law, since delta E thermal equals Q plus W, this is Q equals negative W. Now remember, W is the work done on the gas. So if we're talking about the work done by the gas would be equal to the heat transferred into the piston. All right. And in an earlier video, I alluded to cyclic processes. So a cyclic process is simply any process you can imagine. I'll just draw one, where you end up back where you started. So I'm imagining maybe this one here. And we already saw that the work done on the gas is equal to this area, again with a minus sign if it's counterclockwise, sorry, if it's clockwise, and a plus sign if it's counterclockwise. But the big deal here is that over one cycle, so in general, I mean, these processes, they don't have to be straight lines. They could be, we could connect these dots with anything we want. But the point is that over a complete cycle, whatever these curves are that connect all, however many intermediate points we have, we end up back where we started. Now, as we argued earlier, since the pressure and the volume are the same, that means that we're at the same temperature. The only way that could happen is if there was no change in the thermal energy of the gas after a cycle. That's not to say the thermal energy isn't changing throughout the cycle. It almost certainly is. But over a complete cycle, the change in the thermal energy is zero. And so again, the net heat transferred in is equal to the negative of the work done on the gas, or if you prefer, the positive of the work done by the gas. And here I'm careful to say this is a net heat transfer, because over parts of this process we'll be transferring heat in, and other parts of the process will be transferring heat out. The deal is over the complete cycle, the difference between what's transferred in and what's transferred out is going to be something other than zero. And that difference will be what gives us the useful work if this is a heat engine. Alrighty. So the last of the processes that I want to look at here is a free expansion. So in a free expansion, what I'm imagining here is, again, we've got a well-insulated container. And initially, I have a membrane right here, very thin membrane. There we go. So then this membrane will rupture. And so the gas that was all on one side of the membrane and leaving a vacuum behind will now spread out to go over the whole area. Well, let's think about this for a moment here. Clearly, there's no heat transfer. It's a well-insulated container. There's also no work being done on the gas. What pushed on it? Nothing. We just had this, this membrane fail. Or if we really wanted to, we could just have Scotty beam it out. But that's not going to change one whit. We're not doing any work on any of the molecules. So by the first law, since the change in thermal energy is Q plus W, that means the change in the thermal energy is also zero. And this again makes some sense because if, say, Scotty beams our membrane out of here, we didn't change the speed of any of these molecules at all. So no change to the thermal energy. So strange but true. Now the PV diagram for this thing is weird. This is one of those cases where all I can do is draw the initial and the final state. Whatever it may be. So this actually, so I got this sitting on isotherm here just because so it's not an isothermal process, I'm just drawing in isotherm since there's no change in thermal energy. This is if it's a gas. If there's, again, all bets are off if we have something changing phases here. But the main thing is other than me having those two sit on the same isotherm, I cannot draw a line that connects these at all. Basically, I can just draw a big question mark and just say it started here, it ended there. And this is because this violates the quasi-static process assumption 7 ways to Sunday. So, this is just plain because as this is expanding, there is no well-defined volume. We just have to wait for it to finally settle out in its new configuration. First it occupied this volume, now it occupies that volume. Yeah, that's what we know. We also know that the temperature didn't change, so we know those two dots are on the same isotherm, but beyond that, that's it. We can't draw any kind of a line at all that connects the 2 points. Alrighty, so with that, in the next video, we'll start to worry about things like phase changes and stuff like that. So we'll be introducing specific heats and latent heats and talk about heat transfer. So catch you in the next video.